So in this video we are going to be looking at some tutorials on matrices, and the first one we are going to look at vector spaces, where we are going to be proving that a space which is a set of all 2x2 matrices with real coefficients is a vector subspace. Now the second we are going to look at how to find a null space and the nullity of a matrix, and thirdly we are going to find the characteristic polynomial of a matrix, and then we use these to find the eigenvalues and the corresponding eigenvectors. Stay tuned. So let's begin with the very first question, which is asking us to prove that the space S, which is the set of all 2x2 matrices with real entries, is a vector space of the vector space M, that is all 2x2 matrices with real entries. So to prove that a space is a vector space, is a sub-vector space, there are 7 properties that we need to prove, but some of these properties are embedded in others, so there are 3 main basic properties that we need to prove. Proving these 3 main basic properties is equivalent to proving all those 7 properties, because in those 7 properties, some properties are subsets of others. So the very first thing we are going to verify is if the zero matrix belongs to my subspace S. Now this is my subspace S, the set of all 2x2 matrices with real entries. Alright, so for me to prove that the zero matrix, which is simply the null matrix, meaning all the entries are 0, it simply means that if my A here is 0, then I have proven this this relationship, that the zero matrix belongs to my space S, since S is a set of 2x2 matrices with real entries. So in order to do that, since my A is a real number, I will simply take A to be 0, because 0 is a real number. Taking A to be 0, this matrix transforms to this matrix here by replacing A with 0, and clearly we see that this zero matrix belongs to S, because if I feed 0 here, I'm going to have a 2x2 matrix, and A being a real number, replacing it with 0, the condition is satisfied. Now the second thing we are going to prove is that if you have 2 matrices A and B, which are 2x2 matrices, the sum of those matrices is belongs to my space S. So with that, maybe I can just set my matrix A to be this matrix and my matrix B to be this matrix, and my constants, my A0 and B0 are constants, that is, they're in the set of real numbers. Now what is their addition? Is simply this plus this, and to add 2 matrices of we add 2 matrices if and only if they have the same order, and in order to do that we simply add their corresponding entries. So since all these entries are 0, 0, 0, adding them up gives us 0. Then we just add A0 plus B0 to have the very first entry here. Now we know that A0 and B0 are in the set of real numbers. It means that their sum also be in the set of real numbers. So if I set A0 plus B0 to be equal to C0, then C0 also be in the set of real numbers. So from there I get A plus B to be equal to this matrix, that is replacing A0 plus B0 with C0. I'm just trying to make it to look like this form, so that though we can allow it this way and we conclude, but I'm just trying a way to make the addition to look like this form, and then we conclude that it belongs to my subspace S, because C0 here also belongs to the set of real numbers, as A0 belongs to the set of real numbers. Now the third thing we are going to prove is that if we have a constant K that belongs to the set of real numbers, and I take this matrix here, that is the basis of all the 2x2 matrices that have been given, then K times that matrix will always belong to my space S. So to do that, I just multiply K times my matrix A, K times this. Now to multiply a constant times a matrix, we just multiply the constant times each entry. Multiplying with these entries to get 0, so we just multiply with K with A, and we have this. So with that, we know that K is a real number as we stipulated originally, and A is also a real number as it was given. It means that K times A will also be a real number, because you're doing the product of 2 real numbers. So with that, if we set K times A to be lambda, it is definitely a real number. So we have the matrix this transcribes to the matrix this. Remember, I'm just trying to make my final matrix to look like the original basis of all the 2 by 2 matrices. So we can therefore conclude that this matrix belongs to my subspace because lambda is a real number as well as a is a real number. You see the relationship between a and lambda is obvious. So with that, we can conclude that since a, b and c are true as we have proven, then my S is a vector subspace. Alright, the second problem we are going to look at is find the null space and the nullity of the matrix M. So the null space of a matrix, that is the first thing we are going to look at. It is simply a certain matrix, maybe the matrix U having these entries A, B and C, such that if we multiply it with our matrix M, we always have the 0 matrix. So multiplying M and U, we get our M times U to give us the 0 matrix. Now we can create a system of simultaneous equations, 1 times A minus 1 times C, because the second here 0 times B is going to give us 0, and we equate it to its corresponding entry on the right, which is 0. Now 2 times A, which is 2A, plus 1 times B, which is B, plus 2 times C, which is C, equal to 0. And negative 1 times A, which is negative A, plus C as well is equal to 0. So with that, we can look for A in the first equation. A will be equal to C. In the last equation, A is also C. Now I can replace A with C here, and I get 2C plus B plus 2C equal to 0. So with that, I get A to the C. Now here I have 4C plus B equal to 0, meaning B is negative 4C and C remains C. So my vector U, which is the null space of my matrix M as supposed, can be written as C negative 4C, C. Those are the entries because A is C, B is negative 4C, and C is C. We can factor out our C and we get this. So we can now write our null space, which is a span of vectors, because there are infinite number of vectors in my U is a span of vectors, because we have a constant here which is in the set of real numbers. So for simplicity, I'm just going to change the constant to be any other thing, because I'm trying to avoid like putting the very constant here, which is C, which I can find in my null space as an entry in my null space. I'm just avoiding that. So I can have the null space of my matrix M is the set of vectors, which is lambda times 1 negative 4 1. So this matrix 1 negative 4 1 is simply called the basis of my null space, because it is the very first, that is the building block of all the vectors that are going to be found in this null space. Like I said, the null space here is just a span of these vectors, because we have infinite number of vectors since lambda is in the set of real numbers. Now the second part here, we are going to find the nullity of the matrix M. So I'm going to give you the definition of nullity. Nullity of a matrix is simply the number of free vectors in its null space. Now the number of free vectors in this null space is gotten by letting my constant lambda to be equal to 1. Having my constant lambda to be equal to 1, it simply means that I'm just going to have one free vector, which is this vector. So basically the basis of my null space gives me the nullity of it. Since here we just have one, we can say the dimensions of the basis of the null space give you the nullity of the matrix. Here, setting lambda to be 1, the null space has basis this matrix only 1 negative 4 1, and it is only one of it. So we say the nullity of my matrix M is equal to 1. If we had two of them, maybe this lambda times this matrix plus beta times another matrix, then they are going to be our basis will simply be this matrix here and the other matrix that beta multiplies. So they are going to be two free vectors by letting lambda and beta to be equal to 1, and the nullity is going to be 2, but in this case we have the nullity to be equal to 1. Alright, Alright, so we proceed with question 3, still on matrices. Given a matrix A which is defined by that matrix with entries 1, 2, 8, 1. The first question is asking us to show that the characteristic polynomial of my matrix A is given by P of lambda equal to lambda minus 5 times lambda plus 3, and the second is asking us to find the eigenvalues and their corresponding eigenvectors. So let us begin with the first part, which is asking us to show that the characteristic polynomial of the matrix A is this polynomial P of lambda, written as lambda minus 5 times lambda plus 3. So if we start by letting the eigenvalues of the matrix A to be lambda, then it follows that the determinant of A minus lambda I2 should be equal to 0. Now the determinant of A minus lambda I2 is called the characteristic polynomial. So we just need to find this determinant. Finding this determinant and having the characteristic polynomial in this form, then we can conclude that it is actually true, provided we have exactly what has been given. So I2 is simply the identity matrix of order 2, because our matrix A here has a 2 by 2 matrix. So for this subtraction to be possible, then our identity matrix here must be a 2 by 2 matrix, because to subtract two matrices, they must have the same orders, so that you just subtract their corresponding entries. Alright, so let's look for A minus lambda I2 first before we look for the determinant. So this is A and this is lambda and this is I2. Now this is a scalar, so I just distribute into, I just multiply with the entries of my identity matrix. I get this. Now since I'm subtracting two matrices and definitely they have the same order, then I'm just going to subtract their entries. So I get 1 minus lambda here, 2 minus 0, 8 minus 0, and 1 minus lambda. So the determinant is find the determinant of this 2 by 2 matrix. You just take the product of the elements in the leading diagonal minus the product of the elements in the non-leading diagonal, and you get this expression. From there, we can expand this. We get lambda squared minus 2 lambda plus 1. Then 8 times 2 is 16. And with that, we have lambda squared minus 2 lambda minus 15. It can be factorized into lambda minus 5 times lambda plus 3. The factors of negative 15, that when added you get negative 2, and when multiplied you get negative 15. That's it. So if I set this to be equal to P of lambda, because this is a polynomial, then I can conclude that this is actually true, because since this is a characteristic polynomial and I've gotten its corresponding expression, then P of lambda equal to lambda minus 5 times lambda plus 3 is the characteristic polynomial of my matrix A, and we are done. Now the second part of the equation, we are asked to find the eigenvalues and their corresponding eigenvectors. So we are going to begin by finding the eigenvalues before we find the corresponding eigenvectors to these eigenvalues. So how do we find the eigenvalues? We are going to make use of our characteristic polynomial. So simply the solutions of the characteristic polynomial are the eigenvalues. So if I solve the characteristic polynomial equal to 0, I simply get the eigenvalues. So P of lambda equal to 0, since it's a characteristic polynomial, means lambda minus 5 times lambda plus 3 is equal to 0. Now this is the product of two numbers and it's 0. It means that either of the numbers are 0, because if lambda minus 5 is 0, no matter what lambda plus 3 is, the product will still give us 0. So basically we just equate the two factors to be 0. Doing that, we get lambda to be 5 and lambda to be negative 3. So lambda equal to 5 and lambda equal to negative 3 are our eigenvalues of the matrix A. Now let's see how we can use these eigenvalues to find their corresponding eigenvectors. So we are going to begin with the first eigenvalue, lambda equal to 5, and we are going to let the eigenvector associated with this eigenvalue to be U0, having entries A0, B0. It's a column matrix. So from there, it follows that the matrix A times the eigenvector associated with lambda equal to 5 follows this equation, respects this equation, that is A times U0 is equal to 5 times U0. That's generally. So from there we just input the corresponding matrices, that is A for 1 2 8 1, U0 for A0 B0 time equal to 5 times U0, which is A0 B0. Now this is matrix multiplication, so we have 1 times A0 plus 2 times B0 equal to 5 into A0, and the same thing for 8 times A0 plus 1 times B0 equal to 5 into B0. So with that we get our system of equation. We can now look for A0 and B0. We express A0 in terms of B0. So our B0 will be equal to 2A0 according to the first equation, subtracting A0 on both sides and dividing by 2. Same thing for the second equation. It means that my A0 remains A0 and my B0 is 2A0. So with that I can write my eigenvector, since it was A0 B0 and I've left A0 constant, then writing B0 in terms of A0, I just replace B0 with 2A0. So with that I can factor out A0 and I get A0 into the matrix 1 2. Therefore my eigenvector associated with the eigenvalue lambda equal to 5 is the span of all these vectors. So there are infinite number of vectors in U0 is a span of vectors, meaning there are infinite number of vectors here, but the vector 1 2, that is I plus 2j, is called the basis of my eigenvector U0. Alright, we now move to finding the eigenvector associated with lambda equal to -3, and I've called it U1, having entries A1 B1. It follows the same equation. A times U1 should be equal to -3 times U1, sorry, not U0, times U1. So with that we just multiply the two and we equate. We do the same thing that we did up here, and we get our system. Now we express A1 in terms of B1 or B1 in terms of A1. It all depends on you. Alright, so B1 will be equal to -2A1 according to the first equation and also according to the second equation. So my U1, which is A1 B1, is going to be written as such. I leave A1 constant because I have written B1 in terms of A1, and in the place of B1 I replace it with -2A1. With that I can factor out A1 and I get 1 -2. Therefore my eigenvector associated with the eigenvalue lambda equal to -3 is the span of all these vectors. So there are infinite number of vectors, but still the vector 1 -2 is the basis of, that is I minus 2j, is the basis of my eigenvector U1.